Thank you. Good morning, and welcome to Smashing the State Machine, the true potential of web race conditions. Have you ever seen a vulnerability that made absolutely no sense? Something that didn't just leave you wondering, why would anyone write code like that, but asking, how is it even possible to write code that has that effect? Maybe you even got hold of the source code and stared at it for hours and it still made no sense. And perhaps, if you showed it to someone else, they'd say something like, oh, it must be a race condition. In this session, I'm going to share with you tools and techniques to discover and exploit that kind of race condition. Let's start by surveying what we do understand about this attack class. What race conditions have you seen or exploited in the wild? Maybe things like transferring or withdrawing more than your account balance, or applying a single-use discount code multiple times, or maybe overcoming a rate limit on a login form or such like. One of my favorites that I found a while back is that I noticed you could reuse a valid Google reCAPTCHA solution multiple times within a short time window. And when I reported that to Google, they said, well, thanks for letting us know, but unfortunately, our system is so distributed that we can't actually patch this. And as a result, that technique still works on a bunch of websites today. All of these examples could be classed as limit-overrun vulnerabilities. In their essence, they're all about doing something more times than you're supposed to be able to. But if you go digging through every post on race conditions that you can find, you'll land on one called Race Conditions on the Web by Josip Frankovic. And in this post, he describes 4 vulnerabilities. 3 of them are regular limit overruns, and one of them is a bit different. He discovered it by accident, and it was an issue in Facebook, and it took him and Facebook's security team 2 months just to figure out how to replicate the issue. The symptom was that when changing his email address, at one time it triggered Facebook to put 2 codes for 2 different addresses in 2 different parameters in a single email, letting you forge the other address. Now, reading this post, I had no idea what was going on, but it was clear that this is not a limit overrun vulnerability. And so, last September, 6 years after I read that blog post, I decided to try and figure out what really happened. And I gradually came to realize that the race condition attacks that we all know and love already are just toy vulnerabilities compared to what else is out there. So, in this session, I'm going to show you the true potential of this attack class, tools and techniques to achieve this potential, case studies and a live demo to show some of the insanity that's out there waiting for you to discover it. After that, I will share some all-new Nullcon exclusive research into automated detection of race conditions and attacks on other protocols, and then I'll wrap up, hopefully leaving 5 minutes for questions. On certain slides, you'll see there's a mortarboard icon, and what that means is that I've designed a free online replica of that vulnerability and put it in the Web Security Academy, so you can practice exploiting that issue yourself online for free. To communicate the true potential of this attack class, I'm going to use a multi-step vulnerability. A while ago, I logged into a website and it asked me to select a role before proceeding to the proper application. And so I visualized the state machine for the user's role as looking something like this, and I thought, well, maybe I can jump straight from the role selection page to the application and elevate my privileges. But that didn't work, and I concluded that the system was secure. But actually, this state machine is wrong. Maybe you can spot the flaw in it. It's not zoomed in enough, and it's assuming that this GET request to the role selection page isn't changing the application state. And as it so happened, for reasons that I don't entirely understand, the application was actually creating every session with administrator privileges. And then the GET request to the role selection page was revoking those privileges. So by simply not issuing that GET request and going straight to the back end without even following this redirect, anyone could gain admin privileges. And by failing to zoom in enough, I nearly missed that vulnerability. But that's okay, right? That was just my mistake. Everyone knows that multi-step sequences are a wonderful source for all kinds of terrible vulnerability. And as such, whenever you find a multi-step process, it's really important to zoom in and test every possible permutation really heavily. But researching race conditions, I found myself looking back at this finding and wondering, can we zoom in further still? What if the application had dropped our privileges immediately with a second database statement instead of waiting for us to follow this redirect? There would still be a maybe 1 millisecond time window where we were an administrator, but I would never have discovered that vulnerability. That's a slightly scary thought for two reasons. The first is that, well, that vulnerability could be present in any login form that any of us have ever looked at. It doesn't need to be a multi-step login for it to have this vulnerability. But worse than that, it shows that actually any HTTP request might be transitioning the application through an invisible substate like that, and that could be creating all sorts of serious vulnerabilities. In other words, we all know that multi-step sequences are really dangerous, and with race conditions, everything is potentially multi-step. That is the true potential of this attack class, and with that said, it's time to take a look at how we're going to hack some stuff. So, first off, we need to discover these substates, and to discover them, we need a collision. That means we need two requests, one to trigger the substate or race window, and another that accesses the same resource at the same time. In the example we just saw, that might mean trying to log in and access the admin panel at the same time. However, there's a major barrier which has thwarted this attack class for decades, and that is network jitter, which randomly delays our requests, meaning they arrive at the server at a different time, the race windows don't line up, and the vulnerabilities never get discovered. To solve this problem, I've developed the single packet attack, which lets you make 20 to 30 requests arrive at the server simultaneously, regardless of network jitter. Under the hood, the way this technique works is all about TCP and HTTP. The previously best known technique for finding race conditions was called last byte synchronization. And it takes advantage of the fact that most web servers won't start to process a request until the whole request has arrived. So what you do is you hold back the last byte from each request that you want to send to the server, and you send each of those in a separate packet. And because this separate packet is smaller, it's slightly less affected by jitter and slightly more effective for finding race conditions. But this technique only goes so far. A couple of years ago, though, I was reading an academic white paper called Timeless Timing Attacks. And they were looking at timing attacks, obviously, but they noticed that with HTTP2, you can fit 2 entire HTTP requests into a single TCP packet. And that means that it doesn't matter how much jitter speeds up or slows down this packet, those 2 requests get executed on the server at the same time. And that sounded cool, but there's one issue, which is that really to find a race condition we need more than 2 requests, but you can't easily fit many more than 2 requests into one packet. So what I did was I took these 2 techniques and smushed them together to create the single packet attack. So you send separate packets to pre-send as much data as possible, and by doing that, you can send one final TCP packet which completes around 30 requests on the web server at the same time. I've implemented this in the open source tool Turbo Intruder and also into Core Burp Suite using the repeated tab group functionality. They're both available in the free version. I recommend having a play with it. It's seriously effective. But why is this special? Well, it's out there, it's free, but it's not just our implementation that's going to be available in the long term, because after refining this technique over months of research, it now works on all major web servers, and I can still fit the entire algorithm on one slide. It brings this crazy performance in a parcel that's so easy to code yourself that I think it will end up in all major web testing tools. The reason for that is that thanks to some creative abuse of something called Nagel's algorithm, which is present in all major operating systems network stacks, you don't have to code your own custom TCP or TLS stack to make this attack work. You can just take a HB2 library and bolt this feature onto the site. If you're tempted to make your own version, I would totally recommend that. It's a great learning experience, and I think Golang's HB2 stack is probably one of the easiest to bolt things onto in this fashion. And I'm really looking forward to seeing where other people take this technique in future. To benchmark the performance of this technique, I decided to send a batch of 20 HTTP requests 17,000 kilometers from Melbourne to Dublin. And I did this repeatedly and measured the gap between the execution timestamp of the first and last request in each batch. In other words, how close together the requests arrived on the server. When I took these measurements with last byte synchronization, the old technique, I saw a median spread of 4 milliseconds and a standard deviation of 3. Now, that, to be honest, is quite a lot better than I expected. And I think the reason that those figures are so low is that I was using data centers at both ends of this benchmark. So if you were to use consumer broadband, you'd probably see significantly higher jitter. Then, when I tried the single packet attack, I saw a median spread of 1 millisecond and a standard deviation of 0.3. In other words, the single packet attack is 4 to 10 times more effective at triggering race conditions, and on one real-life vulnerability, I was able to trigger the finding in 30 seconds using the single packet attack, and it took me over 2 hours of attempts to trigger the same vulnerability using last byte synchronization. If you want to summarize that in a single sentence, by eliminating network jitter, the single packet attack effectively makes all remote race conditions local. So, now we've solved network jitter, we're in a much better position to go hunting for some bugs. Now, limit-overrun vulnerabilities are pretty easy to find, right? You just look for a limit and try to overrun it. But when you go beyond that, things get a bit more complex. After spending months doing manual testing and discovering many of the challenges that are out there, I've developed the following 3-step methodology to find these bugs efficiently. You predict where you might have potential collisions, probe those places to identify clues as to whether there's a substate there or not, and finally prove the concept by figuring out what happened and using that knowledge to build an exploit. Prediction is just about efficiency. In theory, we ought to test every possible combination of endpoints on the entire website, but that's just not practical, so instead, you can hone in on places that are likely to have collisions that have serious consequences. After that, we can start to rule out endpoints that have less collision potential. For example, 2 threads editing a single piece of data at the same time could be interesting, whereas 2 threads appending to the same piece of data is less likely to have a useful outcome. Likewise, we can ask, well, are our requests going to edit the same record in the database? For example, if the password reset tokens are stored in the users table, then if we do resets for 2 different users at the same time, two different rows of the table will be altered, and a collision is probably not going to happen. Meanwhile, if the password reset system is storing the token or the pin in the user's session, we can take our session, use that to trigger resets for two different users, and potentially cause a collision, and then if we're really lucky, the reset token will be emailed to the wrong user. After that step, it's time to probe for clues. First, you make sure you recognize a clue when you see one by benchmarking the application's normal behavior, just by sending your requests one at a time, and then you throw them at the application all at once using the single packet attack. What you're going to look for when you send the requests all at once is any deviation from the behavior that you saw during the benchmark, any anomalies. If you don't get any anomalies, they might be secure, or you might just need to tune your attack timing, which I'm going to mention in a little bit more detail in one of the case studies later. Finally, once you've got some anomalies, it's time to understand what happened, clean up your probe and replicate the behavior, and explore the impact. A word of warning on this, if you're doing this methodology right and being ambitious, then you may end up with behavior that is quite weird and unfamiliar and not something that you've encountered with any other exploit technique. And that can mean that the path to maximum impact is not at all obvious. So I recommend thinking of your finding as a structural weakness and looking for other parts of the application that lean on that piece of structure, and also looking for variations, because these issues happen in clusters. So you might have one that has a really low impact, but it's a clue that there's another one right next to it that's more serious. The final point here is, whatever you do, don't stop at the first successful proper exploit that you find. I made that mistake myself during this research and lost out on around $5,000 as a result. Now, let's take a look at a tiny slice of what you might find if you apply this approach in the wild. GitLab lets you invite unregistered users to administer projects via their email address. And I thought, okay, let's test it. When I did my baseline, inviting one address 6 times with a gap in between each, I got 6 responses saying status success and 1 invitation email. When I resent those requests all at once, getting processed in the same millisecond, I got 1 status success, 5 error messages, and 2 invitation emails. So we've got 2 clues here. The first is getting 2 invitation emails from 6 messages is a bit suspicious. And the other clue is the 5 error messages. Now, that second clue, it's worth mentioning, I would not have recognized that second clue if I hadn't done the baseline, because the content of the error messages looks completely sensible in this context. So it's really important to do that baseline step first. Now, using this race, I was able to successfully create multiple invitations to the same address. And I initially thought that was completely harmless, until I noticed that the application only displays 1 pending invitation at a time. So that means I can create a low privilege invitation for a user, and when the admin spots that and goes, they're not supposed to be invited, and deletes it, the application tells them user was successfully removed from the project, and it actually replaces the invitation with a higher privileged invitation to the same user. Now, that impact is okay. It's not amazing, because you need quite high privileges to exploit it in the first place. And it really left me wanting more from GitLab, and wondering whether there was another angle that I could take to achieve a more serious impact. One approach that you can take to finding inspiration for these kinds of race conditions is to look to classic multi-step exploits and then look for a race condition variation. There's a classic multi-step attack that you do on online shops, where you add an extra item to your basket during the payment validation process. And if you time that right, you can get the extra item for free. And I noticed that if you draw the state machine for GitLab's email verification process, it looks awfully similar. So maybe if we change our email address while we're validating our email address, GitLab will end up validating the wrong one. That would be really high impact, because by forging a validated email, I can hijack any administrator invitations that were intended for that other address. So I probed for this, and that didn't yield any clues whatsoever, but I noticed that the email change response was coming back to me after the confirmation response every single time, presumably because changing email takes longer than confirming an email. So I thought, okay, maybe there is a race window here, but it's just not lined up right. And I was able to tackle this issue simply by sending the confirmation request 90 milliseconds after the email change. Now, that simple approach worked on GitLab, but it's not ideal because we're sending these requests with a client-side delay. They're going in separate TCP packets, and that means that network jitter can interfere with our attack. I later discovered an alternative solution that I think is better. Web servers often delay requests that are sent to them too quickly, and we can take advantage of that by sending a single packet with maybe 20 dummy requests in it, in between the two requests that matter. And these dummy requests will make the web server cause a server-side delay for us and make the exploit reliable. So, lining the race window up on GitLab revealed a massive clue. Sometimes when I did this attack, the email confirmation token was sent to the wrong address. This initially looked awesome, but unfortunately, this misdirected code was only ever valid for confirming the already confirmed address, making it useless for any kind of practical attack. But at least it proved that there's a substate hidden inside GitLab's email change endpoint. And it motivated me to dig further. And for this session, I'm going to attempt this via a live demo of a remote race condition using the conference Wi-Fi to exploit a GitLab server hosted in Ireland. So we'll see how reliable it is. Cool, so here we've got GitLab. Just to demonstrate, if I try to change my email address here, then you can see the new address has been set into a pending state because I haven't proved that I own it. And they've sent a confirmation email to that address. So this is the process that I'm going to try to hack. So this is the request that changes my email. This is the input. Okay, so first, I'm going to probe for vulnerabilities. I'm not going straight for an exploit. I'm going to probe by changing my email address to 10 different emails at the same time. And I control all 10 of these emails. So I should see all 10 messages, and then I can analyze those for clues as to whether anything interesting happened. So we should see the responses come back all at once because they were delivered in a single packet. And the first clue, which is a fairly subtle one, is in this X runtime header. Here, I know that this request sent an email. And sending an email is quite a slow process, and yet this only had 400 milliseconds of processing time. So that's a clue that maybe the email is being sent by a different thread. And as soon as you've got multiple threads involved, race conditions become a lot more likely. But that's just hypothetical, right? That doesn't prove that there's a vulnerability there. For that, I'm going to need to check my email. Okay, well, I've got 8 messages, that'll do. So I'm just going to look through these and see if there's anything interesting. Okay, here we go. So this email This was sent, I don't know how big this is on screen, but this was sent to demo1@portswigger.net. But you can see from the contents of this email, this is intended to confirm the address for demo 5. So that proves that there's something sketchy going on here. We've got our anomaly, and now it's time to go for an exploit. Now, this might look like it worked, but this is not a successful exploit because this button, this confirmation token, doesn't work. You see, because I've basically overwritten this token 10 times. There's no chance of this actually working. So now I need to take that clue and move towards something that actually works. So for my exploit, I'm doing 2 things differently. The first thing is that I'm only sending 2 requests to minimize the chance of my token being overwritten. First, I'm setting it to an address that I control, and then I'm setting it to the address that I want to forge. There's no way that the address spoofed at localhost should trigger an email to my Gmail inbox. The other thing that I'm doing is, in order for this misdirected token to actually be valid, you have to trigger the application's email token resend functionality, not their send functionality. And to make that happen, I need to preset it to the same address first. So that means this triggers the resend, hopefully, and sends the token for this to my inbox. That resend bit took me around 2 months to figure out. So let's try this, and then I'll check my inbox and we'll see what's happened. Because we're just sending 2 requests, we're in the exploit phase, and that means things are now a lot less reliable. But I'll give it a few goes. Okay, that looks promising. So the question is, obviously this was meant to go to spoofed at localhost. Does this token work? Right, there we go. So if you look here, you can see this has now been set. It's not pending. If you go to my emails, you can see this is a verified address. And if there were any admin invitations or such like directed at that pending address, I would have just hijacked them and gained access to those projects. So, just to mention, I didn't find that vulnerability on a local installation. I just set that up for the demo. I found that on gitlab.com. And I couldn't resist using it to get hold of the email address albinowaxed@gitlab.com, and you can still view it on my public profile there. So what was the code behind that vulnerability? What could that possibly look like? Well, the vulnerable code path starts out in a really popular Ruby on Rails library called devise. And the root problem is an inconsistency between how they decide where to send the email and what to put inside it. The email is sent to an email address held in an instance variable that's passed directly to the thread that sends it. Meanwhile, the email body is populated using data fetched back from the database via a server-side template engine. And the impact of that discrepancy is significant. It means you can get tokens intended for other users. That means you can hijack pending invitations, and there's another bit of impact too. GitLab can be used as an OpenID provider by third-party websites to create a sign-in with GitLab button. And depending on how the third party does the integration, that means that this vulnerability can potentially be used to hijack arbitrary existing accounts on the third-party site. I reported this to GitLab, and they bountied and patched it pretty fast, and then I reported it to devise, and that didn't go so well. I still haven't seen a patch for this issue over 200 days after reporting it. Now, as I mentioned, devise is really widely used. I would say maybe the majority of Ruby on Rails-based websites with an account management system use devise. And so I went hunting for other bug bounty targets that had the same framework. And what I found is it's really easy to fingerprint because there's an unauthenticated endpoint that you can just match for at /users/confirmation. And because of the way the library is made, the way every website integrates with it is slightly different. So often you need to adapt your exploit to hit different targets. On one of them, they had a visible locking system around the whole thing. Like they would not process more than one email change request at a time, so they were secure. On another target, they were vulnerable, but the email confirmation email didn't say which address it was intended to confirm. So if you just read the email, you couldn't find the vulnerability. And I had to write a script to repeatedly trigger the email, receive the email, parse it, visit the link, and reload my profile in order to find out what had actually happened and prove that the vulnerability was present. And on another target, their change my email feature on the account profile was secure, but there's actually a hidden endpoint that device registers, which could be used to still trigger the vulnerable code path. Now, with that, let's have a look at some other systems. Now, one variation that I found is another token misrouting flaw. So it initially looks similar to the device issue, but the two email change requests could be sent with a 20-minute delay in between them, which is not what you expect with a race condition. After some analysis, what I think was happening is that the server was putting my email change requests on a queue, and then that was being processed by some kind of multi-threaded batch job server-side once every 30 minutes or so. So the effect of that was that as far as discovery of that issue went, the timing of my request was irrelevant. It was just the request volume that triggered the vulnerability. And for me to recognize it, it was impossible to recognize the issue by looking at the response coming back from the server, because the issue hadn't been triggered by the point that that response was generated. It was the emails that gave this issue away. Over the course of this research, I've begun to regard spotting anomalies like that as probably the most important skill for finding race conditions. Now, for my research, I focused on email-based attacks, but where else might you find them? Well, one pattern that you might encounter is partial construction attacks. These occur when you've got an object being created in multiple steps, creating an insecure middle state. One example is this session being initialized here, where for a brief time window, this session has a username associated with it, but it doesn't have a token. Now, this type of attack is going to work better on some languages and frameworks than others, because it kind of relies on the target supporting default or null values and not just throwing exceptions when they're encountered. However, it does have a broader impact than that, and for another example of a partial construction, check out the linked vulnerability found by Natalie Silvanovic in Google's WebRTC implementation. Another angle for further research is to explore the root cause of race conditions, which is the underlying data structures and locking strategies. The classic defense against race conditions is locking. For example, PHP's default session handler is file-based, and it only processes one request at a time in a given session. That means that a website might have a limit overrun affecting their database, but you won't discover it if you send all your requests using the same session, because they'll get processed one at a time. To discover it, you need to send your requests in different sessions. So it's important to recognize when this defense is happening, identify what they're locking on, and try and work around it. The most common system these days is batching. This is where a session handler or an ORM will read an entire object in from the database into a local in-memory copy. And any reads and writes are then applied to that local copy, and then the whole thing is written back to the database at the end of the request lifecycle. That makes them internally consistent during the request lifecycle, but as soon as they pass any data to a background thread, as we saw with devise, everything falls apart. Also, if you've got two requests operating on the same record simultaneously, one will generally end up overwriting the database changes from the other. And finally, of course, some systems have no defense whatsoever, which goes quite badly, especially if a session handler doesn't have any defenses. There's quite a few completely plausible, reasonable code patterns that suddenly have critical vulnerabilities if they're built on top of a racy session handler. Now, when I first published this research last month, I thought automated detection of race conditions was impossible, and so I hadn't tried it. But with Nullcon coming up, I thought, you know what, I'll just try it anyway and see what happens. So I started out with a really basic concept. I just automated the probe phase by sending 10 requests one after the other and then 10 all at once, and just looking at the response codes to see if sending them in parallel triggered anything interesting to happen. And I ran this on my pipeline of 30,000 bug bounty sites and saw pretty much every status code in existence. But by parsing through these, I was able to get some clues as to where there might be issues and where there probably weren't. The first two are kind of generic, you can't tell much from them, so it's probably worth digging further. The second two are basically just saying that the backend has been overloaded, so there's probably nothing interesting there. On another site, the application handled my requests fine, but that was triggering server-side requests to a different service, and the backend service got overloaded, which meant that went down and triggered an error from the front end to come back to me, leaking the address of the backend service, meaning that I could talk to it directly. Finally, on one or two servers, I saw some quite suspicious error messages that suggested maybe my requests were getting malformed, which might indicate some kind of desync attack, but I'm not entirely sure. So this first pass, it found some maybe valid stuff, but also generated a lot of noise. And I thought, okay, let's have another go and try and make something that finds fewer items but more interesting ones. So I thought maybe some servers are getting mixed up and they're sending the wrong responses or the wrong fragments of responses to the wrong people due to a race condition, a bit like the cloud bleed vulnerability from a while ago. So I put a unique canary in every request that I sent to the server, and I looked for that coming back in the wrong response from the server. And that found some legit issues, such as one page which was embedding some JavaScript which had dynamically populated data which often came from the requests of other people browsing the server at the same time as me. It also found a whole bunch of cache poisoning issues, which I wasn't really expecting, but were welcome as well. Now, both of those techniques are available now in an update release just now to /powered scanner. The other thing I thought that I'd look at for Nullcon is whether you can apply the single packet attack to other scenarios and protocols. First off, you can make someone else's web browser perform the single packet attack on itself by abusing the TCP congestion window using a method documented in that white paper. But you can't make the browser fragment requests for you. So with this technique, you're only limited to maybe 2 to 5 requests in a single packet. But if someone manages to successfully exploit a client-side race condition like that, I would definitely love to see a write-up. You might be wondering, well, can you improve this attack that uses HB2 by using HB3 instead? And the answer is actually because HB3 is over Quick, which is over UDP, it's kind of worse for race conditions because you've got this forced maximum packet size of 1,500 bytes, so you can't fit as many requests in a single packet. So I don't think this technique is as good. I haven't speculatively implemented it to prove that, though, because that would be quite a lot of work. Finally, the other question is, well, what about WebSockets? Now, WebSocket race conditions are definitely out there, and looking at this, I initially thought the single packet attack couldn't be applied to WebSockets because you can't interleave fragments of different messages. But then I discovered the wonder that is WebSockets over HTTP2. In HTTP2, you can establish multiple separate WebSocket connections and have them all going over the same HTTP2 connection, which means you can have multiple concurrent WebSocket messages in a single TCP packet and use that for the single packet attack. Finally, as far as defense goes, well, when a single request can push an application through invisible substates, understanding and predicting its behavior is just really difficult. So all my defense suggestions are based around avoiding the creation of substates in the first place. And the foremost way you can do that is avoid mixing data sources. Devise was vulnerable because they sent an email to an address field from an instance variable, but read in the email contents from a database. If they'd taken both values from variables or both values from the database, they would have been fine. Also, obviously, it's great to make use of your data store consistency features like database transactions, atomic operations, and also data layer limitations like uniqueness constraints. And finally, make sure you know what race condition defense system your session handler is using. There's a lot of further reading available. The three key things I'd suggest are check out the white paper, have a practice on our online Academy labs, and then grab my code and see if you can find some real vulnerable systems. If you have any crazy findings with these techniques, I'd totally love to hear about it myself. Just drop me an email. And the three key things to take away are the single packet attack makes remote races local. With race conditions, everything is potentially multi-step. And to find these bugs, predict, probe, and proof. Hope you've enjoyed that presentation. Thank you for listening.
Feel free to ask any questions from James.
First of all, I would like to say hi. It was a really informative session. I would want to ask you a question which I don't know if it holds any credibility or resemblance. But can we use race conditions to bypass intrusion prevention systems and commit DOS attacks on different kinds of sites?
So the question was...
Basically, it's the same thing, right? You're sending like multiple packets, multiple requests at the same time. Could that be used to like do a DOS attack?
I think you could use them to kind of... You can use them to bypass things like rate limits in the short term.
Okay.
Like maybe they say if they send more than 2 requests, then IP ban them. And with this technique, you can get 33, but you can get 30 through, but you are going to get banned after that.
Okay, so imagine if I have a service and it allows me to send 50 requests at a time, and instead of sending normal 50 requests, I embed 50 requests inside of those requests or 30 requests inside of those requests and send them just the way you send them in race conditions. What would happen then?
It might work, but I think the number one thing I would say is with race conditions, it's really hard to predict what will happen. You don't know what's going to happen. That's what makes them so cool. You've got to try and find out.
So you would suggest that like we should experiment